And I think I wrote the problem wrong. V naught should be 5, not 15. So let's erase that so we won't get the wrong answer. And again, it's not letting me erase. Okay. This is supposed to be 5, right, in your book. V naught is 5. Okay, so let's start the antiderivative process. So we are going to integrate this guy, right? So the integral of a of t dt, the integral of 3t dt, right? This is your a of t. And again, you can take out your constant of 3, and you get the integral of t dt, which gives us t squared over 2 plus some constant of integration. Now remember, this is going to give us our velocity function. So we have 3 halves t squared plus c. Now I do want to mention something that in number 11 I didn't do. So in number 11, when we added our constant of integration, I just input, this 5, which works at times. There's special cases, and number 11 was a special case, but it's not always going to be just adding that. That's not always going to be your constant of integration. So in 13 and 16, I'm going to show the intermediate steps. So from here, so we have, right, it's a velocity function. So v naught equals 5, right? Or in other words, when t is 0, right, the velocity starts, it's 5. So we have v of 0 equals 3 halves 0 squared, right? We're just inputting this 0, right? Or that's what this means. And actually the top one, not the bottom one, right? This 0. And v of 0 is 5, according to just our initial conditions. And this is nice because all this is going to be 0, right? 0 squared is 0 times 3 halves. Well, it doesn't matter. Anything times 0 is 0. So, I mean, we do get the 5, but you'll see in 16 that's not the case. So our constant of integration is 5, so we can go ahead and write a particular solution. So v of t equals 3 halves t squared plus 5. So we have a nice quadratic function again. So next step, we want to find the velocity, or the position function. So we're going to integrate this guy. So the integral of, and actually let's write it as, so we want to find x of t, so we're going to integrate v of t dt. So the integral of 3 halves t squared plus 5 dt. And I can break this up. So let's see, I'll take out the 3 halves, integral of t squared dt plus the integral of 5 dt. And again, these are indefinite integrals because we're not getting a numerical value, right? Indefinite integrals are functions, not numbers. A definite integral, you actually generate a numerical value, but a indefinite integral actually gives you a function. So you'll see that on your concept questions. So this is an indefinite integral. Okay, so we can integrate this guy. So we're integrating, that piece, which gives us t cubed over 3. And confuse you here. So I'm integrating that part plus 5t, right? That's a simple integral, right? Integrated this guy and this guy. And again, our constant of integration. This is nice, right? That's really 6 over, 3 over 6. So it's a half. And we have, so x of t equals, let me write my half. So 1/2 t cubed plus 5t plus c. So again, we go back to our initial conditions, and for x of t was, right, 0 and 0, right? When t is 0, x naught is 0, so it really starts at the origin. And again, substitute, right? X of 0, t is 0, times 5 times 0 plus c. But again, that's going to be 0 and 0. X of 0 is 0. So, I mean, c is 0, so we're adding really nothing. So our position function is 1/2 t cubed plus 5t, right? You don't have to add the 0. And that is pretty much, whoops, all right, my x here. So that was a good problem. I'm glad I picked this one. So again, notice the integration is not very difficult. It's keeping everything organized. So again, we started with acceleration, right? We got to velocity function and finally to the position function. So I want you to, let me maybe just write this in color. I do want to emphasize this, right? So you started with acceleration, and then you went to velocity, right? You integrated a of t, then you integrated v of t to obtain your final position function. Okay, hopefully that helped. And the last problem I will do is number 16 in the next video.